Today I'd like to introduce our guest for today, Dr. Anna Rosen, who's a computational astrophysicist. And that's why you notice we have some very special guests in our audience today, the astronomers. They're the ones who look nervous when we're talking about computers. You guys have been Anna is actually originally from LA. And
the Valley, yeah. I'm a Valley girl.
I'm trying to avoid that.
Oh yeah.
Did her undergraduate at Berkeley. She double majored in physics and astrophysics. Then went to UC Santa Cruz. Got her degree in a PhD in astronomy and astrophysics. And then immediately after graduating, she then declined a NASA Hubble Fellowship. Let that sink in for a second. But there she had a good reason, because she accepted a NASA Einstein Fellowship in Harvard. And now is a National Science Foundation postdoctoral fellow and University of Chancellor's postdoctoral fellow over at UCSD. There's a whole list of other accomplishments she has, but if I read them all, we wouldn't get around to the talk. So anyway, let's welcome Dr. Rosen and listen to her interesting talk.
Thank you. Yeah, thank you guys so much. Oh, that never happens. Yeah, no, it's really nice. It's nice to be able to go to my own house after a day of interviewing. So, and of course, seeing the department, my brother went here, so it's nice to come back. So anyway, yeah, so I'm going to discuss a lot of the research I've been doing. I'm trying to understand, maybe we can get the price down a little bit too. So, the nice thing about astronomy is that I get to show a lot of pretty pictures, and also working in computational astrophysics, doing simulations, I get to show a lot of cool movies. But today I'm going to be focusing on discussing the work that I've done in trying to model massive star formation and also star cluster formation. I'm mostly going to talk about massive star formation and the work that I've done to understand how stellar feedback, so that's the injection of energy and momentum by young stars into the interstellar medium or their natal environments, how that can affect their formation and also impact the environments that they form in. Yeah, no, I just came back up.
Keep going. There you go. And then that should work now.
There we go. So here's an example of a little snapshot from a simulation that we've done trying to study. So this is an example of stellar feedback. Basically, as stars form, they give off a lot of mass, momentum, and energy, in the form of radiation and outflows, and also stellar wind. And as you can see, as these stars grow in mass, they actually can blow material away and be quite destructive to their immediate environments. So I'm going to discuss that. So why, first of all, why is this important? Just recently, or last year or two, the Astro 2020 decadal survey finally came out, and this is a report done by the whole astronomical community along with Congress, trying to decide what are the main things, the scientific areas to focus on in the next decade. And this leads to how do we want to use computers or, numerical simulations, and also what telescopes we want to build to answer these questions. And one of the main drivers too, one of the priority areas, is trying to understand cosmic ecosystems, and that is unveiling the growth of galaxy formation. And as I said, they want to focus, on the drivers of galaxy growth, how do galaxies form and evolve. And this also, requires understanding how stars form, and which can be determined with using computational theory. And that's where my research comes in. So just to give some background on how galaxies form, the universe formed with the bang. And here's an example from Illustrator showing structure formation in the early universe. Basically, as the early universe expanded, you had these density perturbations. Some were slightly denser than others, set by dark matter. And then as the universe expanded and cooled, baryons, so protons and neutrons, and also electrons, but those have way less mass, those flowed into the sites of these overdensities, forming galaxies. And so this is, known as like the cosmic red. You look at the dark galaxy here, the dense regions of dark matter is where the baryons flow in. And then as the baryons flow in, you start to form galaxies, and then that gas can continue to cool and you start to form stars. So as you can see here, where the gas density is highest corresponds to where the dark matter is highest, corresponds to where the star formation is happening. Okay, I don't know why this is not working. Okay, sorry. Okay, I think if you take me off as co-host, that would, yeah, I think every time someone pops in. Okay, so just going back to where these stars form. So galaxies, so here's an example of a simulation of a spiral galaxy like our own Milky Way. This is done by Sarah Jefferson, looking at how do these molecular clouds form. So stars form in the densest regions within galaxies, and that's where gas bunches up. Started out as neutral hydrogen, but then as the gas cools and collapses, it is converted to molecular hydrogen, and these are what's known as molecular clouds, or I'm going to focus on giant molecular clouds, and they form in the spirals of these galaxies where the due to galactic dynamics, where and allows these dense regions of gas to collapse and cool very effectively. So GMCs are basically 10 Kelvin. Have these high densities of, so in astronomical terms, these are high densities, and that leads to the onset of star formation within the densest regions within these clouds. And so, for example, as these stars form, and shown in this nice picture of Orion.
The share screen sharing stopped there.
Oh goodness. Okay.
No, you're no longer co-host, so you shouldn't get this thing, but I'm just trying to get that working again.
Oh, here.
Oh, go for it. Sorry to interrupt your flow.
No, that's totally fine. Share screen.
Oh my gosh.
Yeah, I think you have to. Sorry, guys. Yeah, I know it's been over 3 years, right? I think if you go to the your share screen options.
Yeah, you should. You good now?
Yes. Great. Okay. Okay. So going back. So within these molecular clouds, these clouds are turbulent. They're also magnetized, and that sets. These aren't uniform density clouds, and so within these clouds with overdensities, and that's actually the sites of where stars form, and it actually encompasses a tiny volume of the cloud itself. And if gravity was the only, player in this, you would expect all this gas to just continue to collapse and be converted 100% into stars. However, as these stars form, they start to shine, and they also launch jets, and the nearby gas will absorb the radiation and interact with the jets that are launched from these stars, and that will actually heat up and push on the gas, and that leads to inefficient star formation in GMCs, which then overall leads to inefficient star formation in galaxies. So I'm going to focus on massive stars, and that's just because even though massive stars are very rare, so here I'm showing what's known as sorry, get rid of that. I hope so. Yeah, I think so. Yeah. Okay. So if you look at the teal line here, this shows what's known as the initial mass function. So that just basically says for a given population of stars, so let's say you formed a new star cluster, how many of those, what fraction of the stars are of a given mass? And so when I talk about massive stars, I'm talking about stars that are about 8 solar masses or 10 solar masses and above. And if you integrate just over this region over here, you find that only about 1% of the stars of the stellar population are massive. But then if you look at the energy output, which I'm showing here, so this is what's known as the zero-age main sequence luminosity. So that's the star's initial luminosity as soon as it becomes a star, i.e., burns starts hydrogen fusion in its core. Those stars give off the most energy. And so again, if you integrate over this region here, about 97% of the radiation from the star cluster will be from the massive stars alone. So I like to think that massive stars are the 1% of the universe. So when I talk about stellar feedback in star clusters, or in the galaxy as a whole, it's going to be dominated by this radiation and other feedback processes from massive stars. And so they are the main drivers for, affecting, leading to low star formation efficiencies. And by low star formation efficiency, that just means how much of the cloud's mass will eventually be converted to stars. Another thing too is also trying to understand what the maximum mass can be. And so here is R136, which is a young superstar cluster. It's called a superstar cluster because it's very massive, about 10 to the 5 solar masses, and contains a lot of massive stars. And so here, this is so R136 is right here, and you look in here. This really nice paper that recently came out. They were able to kind of figure out the masses of many of the stars within the cluster, the most massive stars, and they find that these stars could be as big as 200, 250 solar masses. And so those stars, of course, because the luminosity of the stars depend on the stellar mass, those stars are extremely bright. And as you can see here, you can see that the effect of stellar feedback from the star cluster has ejected a lot of material. Another thing too for massive stars is that they form very quickly. So because of this, they actually can start to reach their main sequence luminosities as they're actively accreting from their environment. So this is just gravity bringing material in. And because of this, the radiation pressure associated that can be very high, that it can actually overturn the accretion flow. And so another question that we're also very interested in is, can feedback set the maximum mass of stars? And also how may that depend on environment? So for example, our sun, it took about 50 million years to contract to the main sequence, whereas just a 15 solar mass star takes only about 60,000 years. And if you go to higher masses, that time decreases. So these form very quickly. And so stars feed back in their environments in a variety of ways. So the first is radiation, and this is in a variety of ways. So there's radiation pressure, so that's just due to the luminosity of the stars themselves. The molecular gas out of which they form also contains dust, and that dust can absorb that radiation, and it will heat up the dust and also push on it. And then because dust acts like a black body, it's a thermal emitter, that dust will re-radiate. And so in the context of radiation pressure, you have two components here. The first is the first absorption by the stellar radiation field, and the second is this additional radiation pressure due to the fact that the dust will re-emit, and that re-emission will also affect the surrounding gas, like be absorbed by the surrounding dusty gas. The second is that stars will launch jets as they're actively accreting, and then these jets can actually entrain a lot of nearby material and eject material from the burst sites of stars. And then also too, and this applies to massive stars, mostly for stellar winds, in the context of radiatively driven winds. The luminosities are so high that the material in the star's surface can actually absorb that radiation, and that will launch mass from its surface. So this is known as stellar winds, or mass loss from the surfaces of stars. But because these stars are, compact, they have a high escape velocity. So the winds will actually leave the stars, the stellar surface at 1,000 kilometers per second or more. And so since these are really fast, they'll collide with the surrounding gas and actually heat up the surrounding gas. So you get shock heating, and that can heat up the gas to millions of degrees Kelvin, and that gas will adiabatically expand. And then finally, at the end of the star's life, there's also supernovae explosions. My talk is going to focus on these first three because I'm going to focus on feedback that actually occurs during the formation of massive stars. And so the impacts overall, just going back to why studying feedback from massive stars is extremely important in the context of understanding galaxy formation, is that, you look at some of the results from JWST, especially the FANG survey, where some of this work is being done at UC San Diego. This picture broke the internet, and hopefully you can see why. So this is a spiral galaxy like ours, but you can see that it's just covered in holes, and these holes are due to basically star cluster formation and feedback from the massive stars injecting gas. And this is important for the context of studying galactic winds because the integrated effective feedback is going to push on the gas and eject material out. And one thing to note too is that, by looking at these multi-wavelength observations, we can kind of get a hint at what feedback processes may be driving these galactic winds. So if you look here, Spitzer traces like the cold gusty gas, whereas Chandra traces the hot shock heated gas that's produced by stellar winds and supernovae. And you can see that galactic winds are being launched, and you have these hot bubbles, these hot cavities that are entraining the colder gas, and that can lead to metals and dust and hydrogen and other material to be launched into the circumgalactic medium, which is what Kate studies. So stellar feedback from massive stars is very important to a lot of the work that's being done in this room. So just going back, so we use a lot of work has been done with trying to use multi-wavelength observations to kind of decipher the impact of stellar feedback. And so here's an example of that same galaxy, just kind of showing how it looks in these different wave bands. And for us to really understand what we're seeing, it's we need to have a theoretical explanation. So understand the energetics of star formation, how far the reach is, and so on. And then that can help us understand the observations a lot better. So just going back, and so, to one of the main drivers for the Cadle survey, and where I think research is going in the next decade, is that, there's going to be a lot more observational facilities and data that's going to be kind of showing the effects of stellar feedback in the context of galaxy formation and star formation. And with that, we can use computation and theory also to test out our theories and models and then use that to compare. So again, like I said, showing here, I think this is really cool, right? So that is what it looks like without the X-rays. And then once you have the X-rays, then you see that it's that hot gas pushing it out. So what my work focuses on is really looking at kind of like the small scale feedback. So this feedback from individual stars in the context of massive star formation, and also how we can apply that to star cluster formation. And I think that's extremely important so that, we need to really understand the impact of stellar feedback. We need to understand how feedback is transferred from the birth sites of stars, leading to these, giant H2 regions. So here again is R136. And surrounding it is the giant H2 region that's known as 30 Doradus, and you can see this hot gas that's carved out by stellar wind feedback. And then finally, on galactic scales, how these processes actually affect the evolution of galaxies themselves. So, like I mentioned before, comparing these multi-wavelength observations and numerical simulations is ideal because it allows, with astronomy, we can't actually touch any of these things. We have to use telescopes to collect photons, and that can be quite challenging for a variety of reasons. And then based on the light that we see and our understanding of how baryonic material emits photons, we can try to, decipher the physical processes that are happening. And so here's a really nice example that happened on Twitter. Like I said, this galaxy broke the internet when it came out, was also just how using JWST to look at this galaxy, how it compared with simulations. And that confirms that, okay, we kind of have an idea, we know what we're doing. And so numerical simulations are a great way to test our theoretical models and understand the physics behind what we're seeing with observations. So massive star formation itself, so the early stages of massive star formation is quite difficult to observe. The first thing is that massive star formation, massive stars, are very rare, only about 1% by number. And so it turns out that their formation can be quite rare. And they're also far away. So that means, out of the clouds that are forming stars, many a much lower mass, lower density, and they're not really forming many massive stars. And so the sites of massive star formation tend to be farther away from us. They also tend to be highly embedded, the sites of massive star formation, because it's also very quick. And so it's hard to basically do a nice statistical study of this. And then additionally too, massive star formation is a multi-scale. So you're going from the side scale of GMCs down to the birth site to stars. So you're going across many orders of magnitude. And also a multi-physics problem because it involves gravity, turbulence, and magnetic fields, and then also stellar feedback. And stellar feedback, as I showed before, is a bunch of different processes that need to be considered. So we can actually use computers to test, to simulate this. And the way that we do that is we want to solve the hydrodynamic equations. And the reason why we're able to actually use the fluid equation, solve the fluid equations, or treat astrophysical objects as a fluid, even though it's a gas, is also because the mean free path of the collisions between these particles is much smaller than the system itself. And so because it's you have so many collisions, it kind of acts more like a fluid on these macroscopic scales. And that makes it easier for us to solve because then we can use fluid quantities, so gas velocities, temperatures, pressures, and densities, rather than consider each particle by itself. And so this makes simulating these systems computationally feasible. And obviously, like I mentioned before, to be able to star formation is a multi-scale problem. We have to go across many orders of magnitude, so this can be very expensive to do. And so, of course, we have to come up with techniques and methods that can allow us to reduce the computational costs. And so one example is what's known as adaptive mesh refinement. And that's basically, we're solving these equations on a grid, but obviously most of the cloud is not going to be forming stars itself. It's just going to be the densest regions. And so we can just adaptively refine on areas of interest. And so, for example, we can refine on like density, like higher densities, you have more refinement, or in this case, if you have like a shock wave, you can basically refine on the velocity gradient. And this is good for, and this is, a good way to look at, let's say, supernova ejecta and stuff like that. And then also, but in the context of star formation, we typically just refine on the density so that we can reduce the computational costs. So my talk, I'll be going over each of these different feedback processes in the context of massive star formation. So this is a series of simulations I've done over the years to study how each feedback process affects massive star formation. And so I'll start with that. And so I'm going to start with radiation pressure. And so early on, when people first started thinking about how did massive stars form, they first considered radiation pressure. And so, as I mentioned, there's two components to radiation pressure. The first is basically the radiation pressure depends on the luminosity and then the distance from the star. So you have this L over R squared, and that's just due to the fact that the flux from the star drops off as 1 over R squared. The factor of 1 here is for the direct radiation pressure, and then this F trap is like the enhanced dust process radiation pressure. And like I mentioned, dust opacity, the dust is the primary absorber for this, for the stellar radiation field in these dense, dusty environments. And the dust opacity increases as a function of frequency. So that means that the opacity is higher for higher energy radiation from the star. And since these stars are so bright, they're actually very hot. And so the majority of the radiation is going to be at these higher frequencies where the dust opacity is high. And then next too, because these stars are so high, they're also going to give out a lot of photoionizing radiation. And with photoionization, basically photons above 13.6 eV, that is energetic enough for the neutral hydrogen to absorb the photons and emit or eject the electron. That will heat up the gas to around 10,000 Kelvin, and then just due to gas pressure, that will lead to thermal expansion. And so these two different components are associated with the radiation from the star. And then one thing to note too is that as the star grows in mass, and the fact that luminosity tends to go as n cubed, that means that these stars will get very bright very quickly. So radiation pressure can be very significant. I've done some work, this is work led by Grace Oliver, where, we've looked at multivalent observations to assess the different feedback processes, the importance of them. And we find that for these compact H2 regions, so these are around individual massive stars or massive stellar systems, and we find that radiation pressure dominates. And so that allows us to be able to kind of neglect photoionization in these types of simulations. So I'm just going to focus on the radiation pressure and ignore photoionization for now. But with that being said, that means that we want to simulate this correctly. We need to be able to model the radiation pressure accurately. And that actually turns out to be a very tough and expensive problem to do. So here's the radiative transfer equation. It just says if you have a beam of light, with the intensity I, that's just moving through a medium. Once it goes through, let's say, a parcel of gas, that gas is going to absorb some of the radiation. So here kappa is the opacity, and it depends on the intensity of the light. But then also too, that gas is going to also emit radiation. So this is how much radiation is subtracted from the beam, plus what is added to it due to the interaction between radiation and matter. And so obviously the absorption of radiation is going to add both energy and momentum to it. And so with the fluid equations, it basically just describes how a fluid responds to outside forces. And so here with the radiative transfer equation, we want to be able to calculate what is the momentum and energy added to the fluid when light interacts with it. This is a challenging problem to solve on computers because the radiative transfer equation actually has 6 variables. So there's 3 spatial, which is fine, but then there's also 2 angles describing the direction of the motion of photons or the propagation of photons, and then also the frequency. But the net rate of energy added to the fluid is just you can get that by just integrating over all angles and then also over all frequencies. And then same for the momentum, but just, dotted with the direction of the propagation direction. And so that tells us, like, just integrating over the radiative transfer equation tells us the amount of energy momentum that's being deposited. So we can add that to the fluid equations, and you see they are just added to the momentum and energy equations. But then you also get these new equations. This is the radiative energy conservation and the radiative flux conservation. So this is similar to these momentum and energy conservation equations. So going back to the fact that we don't want to have something that depends on 6 different variables, because that's going to make it very expensive. One approximation we can do is taking the moments of the intensity. So you integrate over all solid angles, that tells you the energy in the radiation field. And then again, if you dot it with n hat, that tells you the radiative flux. That gives you the direction of the radiation field. I'm sorry, that F should be bolded. And then finally, if you dot it dot it again with n, that tells you that describes the pressure associated with it. So that is the radiation pressure known as the pressure tensor. And then with that, we get those 2 equations. So the first moment and the second moment describes the conservation of radiative energy and conservation of radiative flux. One of the nice things with this is now we have reduced the effective radiation to 4 dimensions. 4 variables. And now, these numbers are, these quantities are going to change depending on the frequency, right, of the radiation field, because it's multi-frequency. So one thing to do is what's known as the gray approximation, and that is that you just integrate these equations over all frequencies. And for the dusty environments considered in star formation, that's fine, because again, we really just care about the absorption of the radiation field by dust, and then also the re-emission by that. And because it's dust is quite cold, it's going to re-emit basically in the infrared. So doing this gray approximation is okay for the environment. And so this allows us to solve these equations for all cells in our simulations. Now the challenge is actually, how do we treat the stellar radiation field? And like I showed before, the opacity matters. So the frequency of the radiation actually matters. So doing this gray approximation is not the greatest idea. Also, too, it turns out to be a simple problem to actually solve the radiative transfer equation for stars themselves, because we know the direction of the radiation field due to the inverse flux law. So you have a point source, and if the rays or the light is just going to move radially from the star. And so we can actually solve that exactly with the radiative transfer equation. So this just shows the radiative transfer equation along the ray. And sorry, this P just denotes like the radiation, like the number of photons for a given frequency. And then with that, you know, a ray is going to move through a cell, and that is going to then, as it moves through one cell, it's going to have a path length L. And then that gas is going to have a given opacity. And so the energy momentum injected into that cell is just proportional to the original flux times 1 minus e to the minus tau. And so this becomes a easy problem to solve. Now, one of the challenges too is like ray tracing in the simulations is very expensive, because you got to shoot rays from everywhere if you wanted to treat the fluid with this ray tracing technique. So instead, what we do, or what I've done, is basically use that moment method that I described before, because that's it's more of an approximation, but it's less expensive than doing ray tracing. And then for the stars themselves, and to also capture this multi-frequency treatment, because there's way less stars than there are cells, I've done, created this, this new method for adaptive ray tracing, where we can shoot rays from the star, and then as the rays move away, we can allow them to split so that we can serve solid angle, so that reduces the number of rays that we're following. And so doing this compromise for the ray trace saves the computational costs, and then using the moment method also saves the computational cost for the full simulation. So I developed this hybrid radiative transfer technique to be used in numerical simulations, where I use the adaptive ray tracing for stars. And then I use the moment method for the dusty fluid. In this case, I use flux limited diffusion. And then just combine those two techniques. And that gives us both the direct and dust for process radiation fields. And this is just showing kind of how easy it is to do the multi-frequency treatment, because basically we can solve the radiative transfer equation for each frequency bin, and then the total injected energy and momentum of the rate deposition of energy and momentum is just the sum over all the different frequency bins. So doing actually turns out launching rays from specific points within a simulation that is running on lots and lots of processors is a very hard problem. So this involved developing a new asynchronous ray communication algorithm. I won't go into the details, but basically, I designed this asynchronous algorithm where, based on certain criteria, we can allow rays to advance while rays are being communicated, and that reduce bottlenecks, making this computationally feasible for these types of numerical simulations. This shows just some examples of like my weak scaling and strong scaling tests, where we do get pretty good weak scaling and strong scaling results. So weak scaling is basically having each grid or each processor do the same amount of work. So here I just put one AMR grid on each processor with a source at each star, and allowed rays to propagate a little bit past each grid, so that we took into account both communication and also the propagation of rays across these grids. And so I would, this scaled up quite well up to about 1,000 processors. So you get this, that the work goes up, or the time it takes for the communication goes up, depends on n to the point, or to the 2/3. Whereas previous method by John Wise and other, by his work, found that the rate communication went up, depending on n to the 1.5. So we were able to significantly reduce the communication costs, which is necessary to actually perform these simulations. And then also to strong scaling, just kind of describes how basically if you increase the number of processors, keep the problem the same, how does the time it takes to do that computation take? And so here, obviously, so this is just the star at the center of the domain, and I allow the rays to go certain distances. And of course, the more rays you have, the more slitting and so on. It does take longer, but you get very good strong scaling for this problem. And then, of course, when the rays only encompass a tiny volume of the domain, the strong scaling gets worse with time, but still the computational cost is shorter than when the rays go farther. So the nice thing was that this algorithm was able to significantly reduce the compute time for doing this ray trace, and also had better scaling relationships or performed better for the scaling test than previous methods that had been done. So I added my new ray tracing to the Orion AMR code, so the adaptive mesh refinement. And these are just the equations that we saw. These are the radiated hydrodynamic equations. The reason why the energy and the radiation energy equations are so ugly is just because this is what you get. We derive the approximation, the flux limited diffusion approximation by approximating the radiative transfer equation. These simulations, so Orion also contains Lagrangian sync particles. So these sync particles act as stars. They can they create matter from their surroundings, and with that, momentum and mass are added to them. And then basically the stars themselves shoot out these rays, and then the rays interact with the gas. And then finally, too, we also advance gravity, solving the Poisson equation. And so with that, you can now study how massive stars form. So this is showing simulations of two different perspectives, the full core versus a zoom in. And this is just showing the gravitational collapse of the 150 solar mass core. And then a massive star forms. And then as it gets bigger and bigger, you can see how radiation pressure is blowing material away. But the star is still growing in mass. And so, for example, this gets up to about 60 solar masses and could have continued to grow. Oh, and one thing I should note too is here, since I'm using AMR, I chose to refine on the gene density, and that's just basically the size or the density at which gravity is stronger than thermal pressure, so that those are regions that are prone to collapse. So we just refine as much as we can. And then also on the radiation energy density gradient. And that allows us to really be able to have high resolution where you go from optically thin to optically thick regions within here. And that will become important later. So just to summarize, like the main results I got from this work was that, one of the biggest concerns with massive star formation in the context of radiation pressure was that basically the, just from 1D analytical models, it was thought that you couldn't form stars greater than 20 or 30 solar masses because of isotropic accretion. Basically, both radiation and gravity have this 1/r² dependence. So there comes a point when the luminosity is high enough, the accretion flow should just be overturned. And that happened about 20 to 30 solar masses for isotropic accretion. But it turns out that star formation is not isotropic, it's anisotropic. And so basically you just need an anisotropic accretion flow to bring material down to the star. Sorry. And so for here, if you look here, you see that radiation pressure, drives these dense bubble shells. These dense radiation pressure dominating bubbles. But then as they expand away, they can actually become unstable. And they develop these Rayleigh-Taylor instabilities. And that's basically when you have a heavy fluid on the top of the lighter fluid, and you get these, you can develop these Rayleigh-Taylor instabilities that lead to these Rayleigh-Taylor fingers that can actually penetrate through these bubbles and bring material through the star disk system. So that gives you an additional way to have this anisotropic accretion flow, but also to form an accretion disk around the star, a very dense accretion disk, and that also funnels material to the star. So just comparing here, if you look at this shows the spherically average ram pressure. So that's just the ram pressure associated with the infalling material. And again, you see at about 30 solar masses, radiation pressure should overturn that. But then if you look at the mass weighted ram pressure, that's just tracing like the higher density regions. You find that you never that the infalling material has high enough ramp pressure that radiation pressure shouldn't turn it off. And like I said, I only ran this to about 60 solar masses, but you get this one-to-one relationship. So it should have still been able to keep accreting. There's also been a lot of debate about those Rayleigh-Taylor instabilities. And so going back to where you refine matters. So just to go back to what a Rayleigh-Taylor instability is, it's when you have a heavy fluid on top of a light fluid. If you have a slight perturbation, that can lead to instabilities to grow, and those can grow very quickly. And so what I found was that, in comparing to other simulations similar to this that do not get these Rayleigh-Taylor instabilities, is that you have to be able to refine when these perturbations happen. And so by refining on the energy density gradient, so that is what I'm showing right here, and here I'm overlaying the grids. You see that basically when you go from optically thin, which is like the low density bubbles, to optically thick, the shells, you'll have a huge change in the energy density. And so we refine on that area, and guess what? That's where the instabilities are happening. This work here is an example, and like with others, they don't do this refinement criteria. They only refine on the genes density. And so this can explain why we're seeing these instabilities and they aren't. They still don't believe us, but I think in my paper, I think the argument was very convincing, and this shows exactly why. So it's always good to be mindful. Oh, yeah.
When you do the active refinement,
Yeah.
you actually have to move the solution, have to transfer from the coarse part to the refinement one.
Mm-hmm.
That actually complicates the way to solve the problems.
Yeah. Yeah.
And if you don't do that properly, then you may use.
There might be grid noise. Yeah. Yeah. So that could be it too. But the thing too is that this example is from a uniform sphere, so no turbulence. So basically the initial turbulence is going to be the seeds for the Rayleigh-Taylor instabilities anyways. Yeah, but you're right. And the way that this is solved is that we do adaptive time stepping. So you do have to coarsen when you're calculating the fluxes and matching those up. You do have to you could, yes, have like machine level errors and that. Okay, so now I'm going to just briefly talk about the results from including protostellar outflows and also stellar wind. So, but first going in to the results for now, I just want to talk about, basically the impact of feedback depends on how energy and momentum is transferred to the interstellar medium. And that also depends on the properties of the feedback and also how efficiently the gas can cool, because feedback is going to heat up the gas, but that gas can emit and lose energy, and that makes feedback less effective if that radiation is lost. And so both outflows, so these are jets that are launched due to the stardust magnetic interaction, and then also stellar winds, they're both characterized by a mass loss rate and a velocity. And so the momentum added is just the momentum and energy deposited depends on the mass loss rate and the velocities of those winds and outflows. And then the fact is that it will drive a shell of material with mass M shell and velocity V shell. And obviously the impact, if the higher those values are, that just means how more efficient feedback is and how important it is. And there's two cases that can happen. The first is momentum conserving, and that's when you instantly cool. So basically all the kinetic energy is lost. And then you have these quantities for the shell and the shell momentum and energy. But then the other case where it's maximized is known as the energy conserving phase, where you have like no radiative losses. And so that means the kinetic energy is responsible for driving that shell. So basically, the most efficient scenario is this energy conserving phase. But then if you radiate away all the kinetic energy, then your shells are going to be much slower and you're in the momentum conserving phase. So just looking at the velocities associated with these winds, you can get an idea of what phase you'll be in. So this is showing the cooling curve. So that just tells you how efficiently gas will cool. It's a collisional process. So the cooling depends on the gas number density times the cooling function, which depends on the temperature. And so by equating the shell expansion rate to the cooling rate, you can derive a critical velocity that basically, if you're below this velocity, you're in the momentum conserving regime, and if you're above it, you're in the energy driven phase. And this is important because collimated outflows are much slower than winds. So outflows should be in the momentum conserving phase, and stellar winds are in the should be in the energy conserving phase. So that means with stellar winds, that's why you get that hot gas that doesn't rapidly cool, and that we can see in X-rays. Okay, so going back to now including protostellar outflows, this is really hard to model in these simulations because if you want to model the jet launching, that requires sub-AU resolution. So the simulations I showed before, the highest resolution we have is 20 AU, because these are expensive problems to do. And then you also require non-ideal MHD effects to actually have the jets be launched. So what we do instead is what's known as a subgrid model. And what this is basically, it's a subgrid model where you're inputting small physical processes, like smaller than what you than your smallest resolution, to mimic different feedback processes. And so here I'm just showing this is like our feedback model for the jets, where we basically know the momentum and energy being ejected, and then using a weighting kernel, we can launch these in a region near the star. So that's why this weighting kernel has an angular dependence and then a zero otherwise. And here, so the effect of including outflows is that because the momentum is quite strong in these outflows, you can actually drive these large scale outflows that can inject a significant material from the stars themselves. You know, what we also find and others find is that basically the presence of outflows leads to low density cavities where the radiation can escape. So that actually makes radiation pressure less important. And then, oh yeah, and then going back to your question from yesterday, right? It was like, how can we make sure these things work? We're doing things correctly. Here I'm showing, this is a really nice result. Basically, this is just showing the entrained outflow force for my simulations and comparing it to the observational results. So this line here is an observational result showing how the entrained outflows for massive protostars actually depends on the source luminosity. And my simulations agree quite well with that line there. Another thing to note too is what the energetics of the outflows, because the goal is that outside the site, energy momentum will be injected into the larger scales. And so here, you know, what I found is that the momentum in the entrained outflows is about 25%. So we go back to the argument about momentum driven feedback, you expect this one-to-one relationship, and I'm finding that it's less. But that's because too, is that this outflow momentum, so you entrain material, so this is what's known as mass loading. So basically as the jets move out, you're gonna gather mass and that's gonna slow it down. And so it's not, so the argument what I showed before was just taking into account radiation, radiative losses, but this includes also the loss of like momentum due to the fact that entraining material slows the, you transfer momentum to the surrounding environment and slow down the entrained outflows. And then finally, including stellar winds. What I find is that this is actually a very crucial feedback component that no one had considered before. And that's just because as these stars contract, they get very hot. So as these stars are still forming, you know, once they get hot enough, they can actually launch these radiatively driven winds. So this is just basically photons in the atmosphere scattering off the atoms in the atmosphere and then driving material out. And you see that as the star gets hotter, those winds can get stronger here as the star contracts. As the star contracts, it gets hotter, and then you have these end dots. The mass loss increases, but then decreases. But then it drops at around 27 solar masses, and that's just because the physical processes that's driving these winds can change. And so it goes from radiatively driven wind, so that's when scattering in the atmosphere dominates, and then line driven when basically you have the metal ions absorbing the photons. And so that actually drives faster winds, even though weaker winds. But what I find though is that when you have this transition from the radiatively driven to line driven winds, that's when you get the shock heating and you generate this hot gas. You get these hot wind bubbles that then can actually shut off or plunge accretion onto the massive stars. So I find that at about 30 solar masses, winds should be able to shut off accretion, but there are stars much more massive than that. And so what my work suggests, and I think this is in agreement with observations, is that the reason why massive stars are rare is that because of their feedback, they have to form in environments that are very dynamically active. And we're seeing this now with observations. So this is observations from like ALMA, so submillimeter observations and other telescopes, where we're seeing that the sites of massive star formation are having these dense molecular clouds where there is just global collapse within them or filamentary accretion. And so that also suggests that doing these isolated cores,
Isotropy is your assumption.
isotropy for what?
Like wind, yours.
Oh, well, they are isotropic, but I'm not taking into account clumpiness. Yeah, so the fact that the star itself, so both radiation, the luminosity and stellar winds are isotropic. Yeah, and that's because the winds are driven by radiation pressure. Yeah. With that being said, my work motivates too, like moving away from these isolated core simulations and being able to study massive star formation and do the full scale collapse of GMC, so these larger scale environments. And so we're doing this now. So this is with the Starforge collaboration, so star formation gaseous environments. This is not using AMR, instead it's using a meshless method, Lagrangian method, so where we have finite mass particles. And with that, you actually can have go down to because basically allows the particles to expand and contract. So that means low density particles or low density regions are going to have less particles, but bigger particles, and but the high density regions are going to have the particles going to be much smaller. And then eventually we can also, once the density gets high enough, we can place stars there. So remove a gas particle and put a star there, and then model feedback in a similar fashion to what I had described before. And the nice thing too then is that this allows me to also simulate what is happening on these GMC scales and how these different feedback components affect star formation. I think I'm running out of time, so I won't go too much into this, but like I said, this is a different type of method to solve the radiative transfer equations. It uses the meshless finite mass. This is and uses the Gizmo simulation code, and it also includes magnetic fields, radiation, and so on. And one of the nicest things is that this type of kind of geometry or method to solve these equations, rather than doing a grid, allows more flexibility in the size scales that we can probe. And so here's some snapshots from it. So for example, we start with a 20 parsec cloud, so in diameter, and the stars, so where we have sync particles, they have an effective radius of about 30 AU. So that gives us a dynamic scale of about 10 to the 5, which was much more than what I had gotten in the simulations I showed before. And that gives us, the particles are 10 to the -3 solar masses. And so that gives us a mass, an initial mass function, or the stellar IMF limit of 0.1 solar masses. So we can basically study the full IMF. And so just going back to that, this is, we've had a lot of papers come out, but this is one of the nice results going back to what I had described so far, is that basically what we have found is that it requires you have to include all the different feedback components to explain the initial mass function that we're observing in our galaxies and other galaxies. And also too, so if you look here, so it's really, when you include outflows, what we find is that the outflows set the peak of the IMF, so the low mass peak of the IMF. But then you get too many overmassive stars, and so once you include radiation and winds, then the high mass end is more agreeable to what we expect to have. And then also too, this shows when the first O star forms. So this is the first massive star, over 20 solar masses. And once that happens, the feedback becomes significant and star formation starts to plunge. And so basically it's early feedback, so radiation and winds, that is responsible for the low star formation efficiencies and GMCs. One of the problems that we're reaching now is how to basically simulate all GMCs. So for example, this is the antennae galaxies. They are two merging galaxies, and with that happening, it's undergoing what's known as like a starburst, where it's undergoing a burst of star formation. And that's because the gravitational interaction due to these two galaxies merging is leading to these large dynamical inflows of gas. And leading to superstar cluster formation throughout the antennae. And this is a nice result that came out a few years ago, showing basically that, there are GMCs that are as big as, 10 to the 7 solar masses, and those are likely the sites of superstar cluster formation. So the most massive clusters that can form. And that should also have lots of massive stars. Likewise, going back to the LMC that hosts 30 Doradus, and then it also hosts what we think is a proto-superstar cluster. On the other side of it, if you look at if you look at the LMC, you see that 30 Dor, which is a few mega years old, and then N79, which we think is just starting to form now. You see that both of them are at the tidal tails within the LMC. In addition, the LMC is falling towards us. And so what I think is happening is that basically 30 Dor formed first due to compression as it was falling towards us. And then also now N79 is starting to form due to also like these dynamical infalls. And so that's how probably superstar clusters form. And that's why these are also so rare. So they form in dynamical environments. And this is something that I want to simulate with doing these very massive clouds with Starforge. So this is going to also require a huge project with basically trying to modernize Gizmo. So Gizmo right now uses MPI and OpenMP, which helps. So MPI allows for communication across nodes, whereas OpenMP allows for communication within nodes. So that speeds up the computation. However, since this has been developed, there's been a lot of advances in advancing numerical simulation codes using astronomy. And so one of the things that I plan on doing too is to basically update our code along with my collaborators to basically make it way more efficient and scalable and portable so that we can get up to the exascale era and be able to do much more difficult problems like these higher mass GMCs, but also maybe Starforge within galaxy formation simulations, and also maybe start to think about studying planet formation in molecular clouds. And so this will require a bunch of different advances in our code. So the first thing is to move it from C to C++, and then also include task-based parallelism, which allows the asynchronous calls, communication that can speed things up. So you always have the processor doing work, so nothing is left idle. That's speeded up by a lot. Additionally, too, supercomputers are adding more and more GPUs. Those can compute calculations much more quickly than CPUs, and that will also speed it up. And then finally, too, looking into other like parallel computing paradigms, so such as like doing this global memory access for different processors, so that results in less communication. So using stuff like UPC++, and then maybe also, the goal too, because supercomputers have both CPUs and GPUs, and it varies between which computer you're using, making this a hybrid CPU plus GPU code with these advances. And so I'll just leave up my conclusions. Thank you.
Right, when you talk.
Going back to your how to make stars slide, what's it mean when an environment is dynamically updated?
Yeah, so, going back here, so one thing that we found in these simulations, so the nice thing about this being Lagrangian code is we can, and the particles have numbers. Whenever a star forms, we know what particles are accreted, so we can actually trace back, we can kind of like rewind where all that material is coming from. And what we found is that the low mass stars accrete very close to their environment, so they're not having large scale accretion. Whereas where the sites of massive star formation, those take longer to form and the material is coming from much farther away. And so when I mean dynamical environments, going back to this picture here, so in this paper that I'm on with Adam, for example, these lines here are dark filaments, they're infrared dark filaments. But using ALMA, you know, because you get the velocity information. What we found is that, and then from the outflows here too, the energetics of the outflows, we can get an idea, an estimate of the accretion rate into the stars. We found that basically the material that's being fed in through these filaments to where the stars are accreting material or being born is about the same as what the stars are accreting. So I think what's really happening now is that also explains the rarity of massive stars is that you have to have infalls, like due to gravity, bring material in, and then also too, like, you know, the Rand factor of the material, which is the density times v squared, the velocity of it, the infall. So the velocity is high and the density is high, then the Rand pressure is strong enough that the feedback should be less important. And so you can continue to feed material to the stars. Yeah.
Thank you.
You're welcome.
Yeah, during your massive star creation simulation,
Mhm.
it showed that, you know, that process, but there are a few other little dots that appeared.
Oh.
What's happening?
Those are low mass stars. So basically, once we reach the highest resolution, when you go above the genes density or the, you know, on the highest level, we can't follow the collapse anymore, so we put a star there. Now, like I said, those sync particles are like, in that simulation are like, well, the sync radius is 4 times the minimum resolution. So the sync accretion happens within 80 AU of the star. So one of the challenges in these simulations that I definitely want to work on, because it's important for understanding binary information, is when to decide when stars merge. So basically what happens is I end up with a very massive star that forms first, but then, and then an accretion just forms, but then that accretion just fragments into these low mass stars. And basically above a certain mass, once the star should be like, you know, several, you know, solar radii, so quite much smaller than a resolution limit, we don't know if they're going to merge or not. So that's another thing that I want to work on with when do you decide that happens. And yeah, people get very excited about that. And, oh, look at all that. And I'm like, I don't trust it. I mean, I do trust that it just fragments and you can form a companion star, but because of the resolution limits, it's hard to kind of say what happens after that. Yeah.
By approximating the system as a fluid, what do you lose by doing that, and how big is that effect?
Actually, I don't think we lose too much. I think just based on that. So basically, so you take like a fluids class. So and this is, if you derive the fluid equations, it's based on, you have to have like the gas particles have to have a thermal distribution, or they have to have a distribution function describing the motion of the particles. And because these are, you know, they have a thermal distribution, like I was like back in the StatNet, right? Basically it has a thermal distribution that like peaks around the temperature or whatever it is. And then with that, then because it follows this trend, that leads to the derivation of the fluid equations. So as long as the system in question follows that, then doing the fluid equations is a good thing. Is like, it's, no one ever complains to you. Now, the other thing though is that other things you can't do that with. So for example, cosmic ray simulations, like trying to look at the, how cosmic rays move in the plasma. So plasma simulations, you can't always do the fluid equation. So they use a different technique, it's like particle entanglement. Don't know too much about it. So it's more of, the nice thing with astrophysical systems is that most of them you can do this, but you can't do it with all. So it's just, because these are thermal particles, they follow thermal statistical distribution like their movement. That's what allows you to approximate it as, that's what lets you derive the fluid equation. And treating it with those macroscopic quantities instead of doing microscopic, focusing on the microscopic properties. So that would be impossible to solve like this. Yeah.
When you do the ray tracing,
Mhm.
so do you know where you start? And
Yeah.
you know where you end?
Oh, yeah, no, yeah, not at first. So, with the ray tracing, every time, so basically I have to calculate going here. So in every cell,
No,
I-
like this is a yes or no question. You don't know.
no, yeah, so basically I just subtract what's absorbed, and then by the time like 99% of the flux is absorbed, or the luminosity of that ray is absorbed, then we kill it. Yeah. So that means it gets more expensive as the simulation evolves, for sure. Mhm.
For the first there are bipolar outflows, do the simulations also modeling the magnetic fields? Because there's like comfort, for small
Mhm.
mass, the orientation of it is important, right, for the magnetic fields.
Yeah. Yeah, so actually, I'm working with a collaborator on this now. He's doing these really nice, very high resolution, just focusing on the magnetic field of the stars. So like that movie I showed before, the jet launching simulations don't include the magnetic field of the star. They just, the fluid is magnetized. So you have an accretion disk that's magnetized, and it's the it's basically conservation of angular momentum, because my magnetic field is going to wants to remove angular momentum away, and that's why you get the jets. And so accretion is trying to push angular momentum in, and so it's just going to be magnetic interaction with the star and disk, but through the disk magnetic field. That basically the twisting of the field lines.
It's not able to do it, just yet.
Sorry,
So it's not able to do it so far.
what do you mean?
You will be modeling the magnetic field.
Oh, yeah, so this is another project, a collaborator of mine, he's running these simulations, and I'm working with him on it. Where he is studying when you do have a magnetized star with a bipolar field, how that launches jets early on. So we are working on that right now. Yeah, those simulations are being run actually right now. Yeah.
I was wondering, there is this evidence. Maybe most people believe that, in like early twin galaxies, we have a lot of matter.
Mhm.
And so I was wondering if you think that these larger scale simulations that you're planning for the future could potentially explain that kind of scenario.
Yeah, so it depends on how, so basically we defined our IMF completeness limit 100 times the mass of the particle, right? So that's why, I said that the mass completeness limit is 0.1 solar masses, because our particles become the -3 solar masses. So probably the easiest thing would be to do this simulation again, but with much smaller particles, rather than do these massive clouds, like 10 to the 7 clouds, because that means we need 10 to the -10, right? So with that means that if we speed it up enough, then we can do that 20,000 solar mass cloud and have the particles be 2 orders of magnitude smaller, and then we get the smaller mass. So that would give us 0.01, and that can also let us know, can you form, follow how maybe you have white dwarfs form, or do they form in isolation, like do the fragmentation like stars, or also even rogue planets, are those ejected, or are they formed, so like, yeah, so that's the thing, is the goal is, there's a lot that will come out of it. We can do the very massive clouds, but that's going to lead to a higher cutoff. Or we can just stick with what we're doing, when I'm gonna say and, this is stuff we'll do, once we speed it up. And then also probe the low mass energy.
This is a question online, from Matthew Portman. Does neutrino flux play a role in massive star formations?
No. Well, no, because yeah, the neutrinos only become very bright during the supernova, right? There's not much, and then there's so little mass. Yeah, we never, yeah, we don't think about neutrinos during star formation. Yeah.
Well, I had a question to follow up on Kate's question. So I remember reading, but I could have misunderstood, that in the early universe, you also had more supermassive stars.
Yeah.
Due to the low metallicity. Is that the correct understanding?
Mm-hmm.
That would change that, so, if I understand what you're saying, with what I've been hearing, that, because that changes the isotropic limit, is that correct?
Well, it depends. So there's actually, I'm working on a project right now on that, not using these simulations, but I want to include supermassive stars in these simulations. There's a lot of cool work trying to understand what could be the seeds of supermassive black holes, and that's, supermassive stars. And the context of feedback is that, you think that you can't build these supermassive stars, because feedback, you get back down to the expected radii, feedback will blow material away and use accretion. But there's been a lot of good work, like protostellar evolution modeling under these very high accretion rates, like 10 to the -1, solar mass, and so on, where the idea is that in the very early universe, the first stars sort of formed in these low mass halos, like the first class of halos, and then you bring in the baryons, and that leads to these really high accretion rates. And it turns out the protostellar evolution of the stars actually, the higher the accretion rate, the more bloated the star gets and the longer it stays bloated, which means then you have very, even though you have a high luminosity, because the luminosity goes as r²2⁴, you're so bloated that your temperature is so low, so it's low frequency radiation. And so you're not hot enough to launch photoionizing radiation, you're not hot enough to launch winds, and also you want to have winds because winds require metals, right? And so the nice thing about that work is that looking at the context of supermassive black hole seeds, is you can continue to grow, the star just stays bloated, so you can get up to 10 to the 4 solar masses, but then GR effects take over and then you have direct collapse and build a black hole. So everything goes into the black hole, and so you should have massive black holes, kind of roughly 10 to the 4 solar masses, and then if they grow enough, that could be the origin of supermassive black holes that we see today.
But so the lack of metallicity affects the stellar winds, which.
Yes, exactly. Yeah, so they're line driven. Yeah. But at the same time too is once you start to have metal, you have dust, then once you become important. So I think not top 3 stars, but like the generation after that, even when you have some metals. So I'm looking at smaller accretion rates than that, like taking their work and doing my own 1D models, and see how the radial evolution protostars depends on the accretion rate, and that way, and then looking at the feedback effects where then you can build these more massive stars, not up to what they're doing, but like in between, and then also looking at the wind properties.
I don't know if this makes sense, but so you're looking at a really big perturbation and kind of fluid continuum. Are there any problematic issues with the boundary of your simulation for that?
With the bound, not necessarily. I mean, the thing is our initial conditions are highly simplified. Like that was, in both simulations I showed, like it's a sphere. It's almost not a perfect sphere. And then at the same time, these positive turbulence, we have to put that in by hand. So realistically, I would say the main oversimplification is not the boundary conditions, but the initial setup of like the density distribution, the velocity or turbulence distribution of these objects. So we've developed other initial conditions where we can still have like a sphere, but then we drive turbulence for a bit. So we have more realistic density distributions at the beginning. But another thing too is like with scaling up the code, then we'll be able to do this. So Gizmo, there's the Fire collaboration that has done a lot of work on feedback in realistic environments. that have done galaxy formation simulations, and so right now, like Phil Hawkins, one of my collaborators, that he invented Gizmo, and has done a lot of this work. He's looking now, he's been running like a simulation of galaxy formation and looking at star cluster formation near within the nucleus of the galaxy, or the nuclear region of the galaxy. But we're able to do like one star forged star clusters, but we can do more with speeding or scaling up the code, like making it faster and better. Then we can probably do more star forged clusters, but then these galaxy formation simulations, and then that will make our initial conditions less ad hoc. So and also the boundary conditions we use, like the inflowing, like the radiation fields at the boundaries, that is based on like observational constraints and all that. But of course, it's isotropic, which, yes, there's ways that we can also vary that to see how dependent our simulation, our results are to that.
Okay. Yeah, maybe there should be a lot of questions.
In your Lagrangian simulation, what's the computationally most demanding step, and how does the cost scale with the system size or like number of objects?
Oh, God, I don't remember. I have to look at the methods paper. So radiation is always the most expensive. So with StarForge, we use what's known as the M1 method, which is another approximation. So it's another moment method, but it's like first order, whereas flux limited diffusion that I used in this individual massive star formation simulation, we use flux limited diffusion. One thing too, so radiation is always tends to be the most expensive. And then of course, I think it might scale as n to the third to the number of particles. I can't remember. So obviously, the more particles you add, the more expensive it gets. Which is why we have to be choosy with like what our resolution is, like what our particle resolution is, and then also what our and that sets our max. So like one thing I can do is look at do these higher mass clouds, but then reduce increase the IMF components, right? And with another reason why the radiation is in that simulation is the most expensive. Or another limitation of what we use is we use what's known as the reduced speed of light approximation. And so it solves the radiation stuff explicitly, not implicitly. So that means the time step depends on the speed of light. So if we increase the speed of light, so like for example, we in that simulation use 30 kilometers per second, which obviously the speed of light is 3 reduced to the 10. So 30 is like 3 times 10 to the 6 centimeters per second. Right? Yeah, 5, yeah. No, sorry. Okay, anyways, we're off by order of magnitude when we do the speed of light, but in those dense dusty environments where basically you're going to have diffusion with the photons, having a lower speed of light is not a big deal. However, in these dense clouds, we have high turbulence and so on, you have to increase the speed of light. So if you increase it from 30 to 60, then that means that you take twice the number of time steps for to do that same radiation solve time step that you did before at 30 kilometers. So that doubles it. So we have to be choosy with all these different things so that we can actually like run it in our lifetime, but also make it this right.
Well, thank you for a wonderful thought.